Okay, everybody, you're all very welcome to Engineers Ireland here, either in Clyde Road or those dialing in on webcast. You're very welcome. First and foremost, I'll ask people to turn off their phones or at least put them to silent, please. And then if you guys in here in Clyde Road can take notice of two emergency exits to my left here and at the back of the hall. For those here for the first time, again, you're all very welcome. So as part of the Engineers Ireland Energy Environment Division, we typically run 7 to 8 evening lectures the first Wednesday of each month, all year from October to May, excluding January, and we run a number of breakfast briefings, seminars and other events. So I suppose if you like what you hear tonight or otherwise anyway, if you keep an eye out on our events page on the Engineers Ireland website, and there'll be other future events coming up. So moving into tonight, the presentation is titled The Potential for Negative Greenhouse Gas Emission Technologies in Ireland, and it's going to be co-authored by Professor Barry McMullen, Professor Michael Jones, Dr. Alwyn McKeever and Paul Price, who's a research assistant. So if we can run through the presentation, and then at the end we'll have a hopefully a little while for some Q&A. And I'll hand it over to you. Sorry, Barry. For those on the webcast, if you have any questions you want to email in, you can email them in at engineerswebcast@gmail.com. So engineerswebcast@gmail.com, and that's all one word. Thank you, Barry.
Thanks a million, John. Okay, you set me up nicely now. If there's no audience for future talks, it's all McMullen's fault. So anyway, look, you're all very welcome. Thanks very much for the opportunity. Thanks to John and to Engineers Ireland. It's my pleasure to be here. So I'm presenting on behalf of this research project, generously funded by the Environmental Protection Agency. The acronym is IENETS. And the project's objective is to investigate the potential for so-called negative emissions technologies, or NETs, in Ireland. There's a website there. We'll put that back up at the end. I just briefly, John's already mentioned the team. They're all here with me tonight. I'll run through the presentation, but my colleagues will happily join in with the Q&A as appropriate when we get to that stage. So I'm Barry McMullen. I'm based in DCU. I'm an electrical engineer, and I'm the co-PI on the project, along with Mike Jones from Trinity College, Dublin. The two other people working full-time on the project are Alwyn McKeever and Paul Price. So it is a collaboration between DCU and Trinity. Okay. So just what have we got ahead of us tonight? The big picture. We're trying to get into the Christmas vein here. One of my favourite Christmas movies, The Wizard of Oz. But if you take nothing else away from tonight, this line that you're not in Kansas anymore. We're in a different world, and we need to talk about some of the implications of that different world. And the talk about negative emissions technology is part of what is now happening. So the general layout of what I'm going to talk about, we're into the climate change end game in a sense. The human-caused climate change has been triggered by the Industrial Revolution, if you like, but it's gained speed in the last 50 years. And we're now approaching the point where, as I say, we're kind of in the end game. And I want to outline the understanding of that and why it's leading to this discussion. Obviously, there is still uncertainty about how things are going to pan out, significant uncertainty, but I'm going to suggest that uncertainty is not our friend as such, and procrastination should be considered harmful. That's for any software engineers in the audience who know that Go-To is considered harmful. But anyway, that's an in-joke there. Negative emissions technologies are one speculative tool that might be in our toolbox, or really a collection of tools that might be in the toolbox. And I'll just talk about what they are and whether we want to use them, whether we want to be forced to use them, that kind of thing. I'll deal with the specific opportunities or challenges for Ireland. What's Ireland's fair share of dealing with this global challenge? I'll present the specific, not all the options, but a selection of the top options for negative emissions technologies that are most relevant to Ireland. And there'll be a few parting thoughts at the end to hopefully stimulate the questions when we get to that stage. Okay, so this topic is actually, in the last maybe 3 years, in the academic world, it has ballooned. There's an almost literally exponential explosion in publications in the area of what's being called negative emissions technologies, but it's also now penetrating into mainstream media. So this was an article in The Economist just a couple of weeks ago. The headline was "What They Don't Tell You About Climate Change." And you know, the subhead gets it in a nutshell here. Stopping the flow of carbon dioxide into the atmosphere is not enough, or is no longer enough, or at least there's significant suggestions to that effect. We're getting into the situation where, because we've procrastinated so long, that actually extracting carbon dioxide back out of the atmosphere may be an essential piece of climate action, and in the quite near future. Okay, so the modern or the most recent understanding of where we are at in the climate change story, and getting into the climate change endgame from the IPCC AR5 in particular, this concept is now crystallized out of a global carbon budget. And the basic idea is that carbon dioxide is not the only contributor to human-caused climate change, but it is the single most significant, and it's a long-lived gas in the atmosphere, so it accumulates. So as we put it in the atmosphere, it stays there potentially for a long time. A significant fraction of it stays there up to thousands of years. It's a very long time on human timescales. The result is that the atmosphere essentially is almost full. In terms of the carbon dioxide loading that can be tolerated for any given level of climate disruption, the atmosphere is now almost full of carbon dioxide. Or putting it the flip way around, there's only a very limited, finite remaining capacity of the atmosphere to safely take further carbon dioxide loading. And that's the so-called remaining global carbon budget. And because it's cumulative, every year we continue to release more carbon dioxide into the atmosphere, that budget is declining. And it's a budget with a number. Now there's an uncertainty range in that number, but the AR5 report, the assessment report 5 from 2013-14, produced a range as of 2012, but further emissions since 2012 have to be taken away from that, so you have to adjust that range. So right now the suggestion is that numerically, given the Paris politically agreed temperature goal of limiting warming to well below 2 degrees, and that's not just an arbitrary making up choice. A lot of hard, concentrated thought went into it, and basically reflects the risk assessment of warming going significantly above even 1.5. So the number you get is somewhere between 590 and 1240 gigatons of CO2 remaining capacity for further emissions of carbon dioxide on a global basis, which sounds like a wide range, but it's not really all that wide. Okay, so to probe the scenarios for how we use that finite remaining capacity, when it's gone, it's gone. Okay, so it's not going to last forever. In fact, it's not going to last very long. But one way of very crudely thinking about different ways of using up that budget is to look at so-called exponential mitigation pathways, where emissions get ramped down essentially in an exponential way. Why do we choose an exponential curve? And there's lots of different pathways one could imagine, but exponentials are one simple way of talking about it because they're characterized by a constant year-on-year percentage reduction. So if you have a constant year-on-year percentage reduction, what you wind up with is an exponential pathway. And the characteristic of an exponential pathway is that it has the minimum maximum year-on-year rate. Okay, so for any given budget or quota, which is going to be essentially the area under whatever your emissions pathway is, basically if you add up this year's emissions, next year's emissions, the following year's emissions, you get the area under the curve. So for any given area, you then ask, well, what's the pathway that gives the least year-on-year challenge at any point along the pathway, the least fractional reduction, well, mathematically that's going to happen when you have the same rate of reduction all the way through as the least value, and that's the exponential curve. So it gives you the minimum challenge any year. Now whether the year-on-year reduction is an adequate representation of the level of challenge is another question, but very crudely it gives you a starting point. It's important to remember that in looking at any of these emissions pathways, we're talking about year-on-year reduction. So you've done a certain amount of reduction this year, you've got to bank that and do further reductions next year, and then bank that and do further reductions the following year. We have to get down to zero. Until net emissions, net human CO2 emissions hit zero, then the atmospheric concentration continues to increase. The quota continues to be depleted. And as I say, we now have numbers or a number range on what the remaining quota is. Okay, so that's just the concept of an exponential pathway, and I need that just to lock in what I'm going to talk about next. This is not an emissions pathway. Just to flip your brains a little bit. You can now ask a question. Given the global carbon budget, okay, given the range of carbon budgets, how quickly, if we take this minimum maximum rate, how quickly do emissions have to fall? And if we had started, back in 1970, they wouldn't have had to fall all that quickly at all. Okay, but we didn't start back in 1970, we didn't start back in 1990, we didn't start in 2000, we didn't start in 2010, we still haven't on a global basis started. Emissions flatlined, or at least reported emissions of CO2 flatlined for 3 years in a row, but went up again last year. So far from actually declining on a global basis, emissions are continuing to increase. If we had started from 2015 onwards, for that range of quotas, for the maximum quota, if you take the maximum end of the range that the IPCC have quoted, then the exponential reduction rate that would have been required was 3%. But if the more conservative minimum range, the more prudent range, then we would have had to kick in global emissions reductions at 6% per year from 2015. Okay? The point of this graph is simply to show that each year of delay dramatically increases the rate of reduction you need. Okay? So that's the way it was had we started globally in 2015. If we achieved not merely flatlining but reducing, we could have got away with somewhere between 3 and 6%. But each year that passes by, that goes up rapidly. And although there is this range of uncertainty, in time terms, in terms of really getting serious about achieving global emissions reductions, that really only is maybe a couple of decades of uncertainty at the outside. If we strike lucky and the planet doesn't heat quite as quickly as it otherwise might, it might buy us an extra 10, 15, 20 years. If we're unlucky, we've already used that time. Okay, that's the only point of that slide. Time, the uncertainty is there, but it's not really in our favour. It sounds like a big uncertainty numerically, but time-wise, in terms of getting into really aggressive global CO2 emissions reductions, it doesn't make a huge amount of difference. The other thing just to mention, and it's an important aspect of the global or international cooperation which is essential to addressing this problem, is that in the Paris Agreement, the wealthy nations, which are also the high emitting nations by and large, on a per capita basis, the wealthy nations have agreed as part of that process that they have to act first and act deepest. So if these are the kind of, if we need a global emissions reduction rate of 4% per year every year from here on, that means that the wealthy nations have to do better than that, significantly better than that. Okay? If we really need 6%, wealthy nations need to do significantly better than 6% because they're significantly more responsible, both historically and in current terms. That's the agreement. Okay. The concept of negative emissions and the trouble with negative emissions. So I described the exponential pathway as getting you in the smoothest possible way, stretching your quota to the maximum extent over time. Okay, it's really trying to husband that finite quota and use it over time and manage your effort so that you're not suddenly having to do a lot more effort later on. And it's an intergenerational justice question as well. Okay, we should do at least as much as we expect our children or our grandchildren to do. We shouldn't be backloading the level of challenge. However, in the IPCC AR5 report, the set of global emissions reductions pathways and scenarios that are in behind that in support of achieving that the 2 degree target or well below 2 degrees target. This is a slide that is sort of a summary of those. This black line is the one to focus on. So we've got global emissions up here. The black line is essentially an average of the scenarios that would keep us below 2 degrees. But that's not an exponential curve. First of all, it was continuing, relatively flat at 2015, but then getting into serious reductions from about 2020, okay? But it's not an exponential curve, okay? It's actually going below zero, somewhere around 2070 or so, okay? What that reflects is that most of these scenarios actually assume that we won't succeed in cutting carbon dioxide emissions, actual carbon dioxide emissions to the atmosphere fast enough, okay, that they'll actually persist at a level above where they would need to be, okay, and in order to, essentially before the planet notices, it's a big planet, it takes time to warm up, so in order to still keep within the temperature goal, we need to plan later on in the century to be very rapidly removing carbon dioxide from the atmosphere on a net basis globally. Okay, so that's why that black line is actually not merely coming asymptotically to zero, but going below the axis. Okay, so already baked into the scenarios that global policy is relying on is an assumption that on a global basis we will be sucking carbon dioxide out of the atmosphere at significant rates, up to 10 gigatons a year by the end of the century on a net basis. Okay, that is kind of scary enough in a sense, but 2070 sounds a long way away, and a lot of technological development to go on between now and then, and so on and so forth. But when you actually unpick those scenarios in more detail, and this is the real trouble with negative emissions, hidden behind those scenarios is not just that on a global net basis we will have negative emissions by about 2070, but that starting as early as 2030, this is the scenarios for gross emissions. Okay, so the gross emissions are already diverging from the required net emissions from about 2030 onwards. Okay, so as early as 2030, the scenarios are suggesting we're already deploying, or somebody in the world is already deploying, significant amounts of carbon dioxide removal. Okay, that's only 14 years away, 13, 14 years away. Okay, it's not a problem in the dim, distant, far end of the century. Okay, the scenarios we're currently working with are assuming that this stuff is already running within a decade, certainly less than 2 decades, and ramping up to very substantial scale by the end of the century. So we'd better figure out whether that is feasible from an engineering point of view, how much it's going to cost, what the limitations to it are, get the pilot systems running, get understanding out of that. That all needs to happen very soon. Final thing just to point out in this chart, of course, is that was the IPCC AR5 scenarios where basically a starting point was approximately 2010. The world obviously has evolved since 2010. So in fact, the actual emissions and indeed the approximate pledges from the Paris Agreement are not on that black line. They're up here. Okay, so we're already departing from that scenario. And the tacit implication of that is an expectation of doing even more on the negative side. The less we do in terms of actual gross emissions reductions, the more we are buying into a future reliance, and a not very far future reliance, on sucking carbon dioxide back out of the atmosphere and putting it somewhere safe. Okay, that's the global story. What does it mean in Irish terms? This comes from the National Mitigation Plan, based on EPA data published last summer. It's looking at CO2 only. It's not even all CO2, it's CO2 in the so-called electricity generation, built environment and transport sectors. They've been pulled out for special treatment in the Irish policy landscape as a group. And this, I put up this chart because it was put in the National Mitigation Plan for a particular reason, which I'll explain in a second. But basically, this is historical emissions up to 2015, so from 1990 to 2015, and then the EPA projections through to 2035, and the policy commitment for 2050. The current policy commitment for this sector in Ireland to 2050 is to achieve a reduction of 80% compared to 1990 levels. Okay. So in the National Mitigation Plan, they showed, well, if we had started back in 1990, trying to get to that end point in 2050, and we did it, say, on a linear pathway. Now, as I've already explained, a linear pathway isn't necessarily a sensible choice, but if you try to do it on a linear pathway, we would have had to reduce that sector by about 340 kilotons per year, every year, okay? But having not started in 1990 and delayed to 2015, the required reduction rate has gone up to 750 megatons per year, every year, okay, on 30 megatons a year. It's a significant fraction. If we didn't make significant policy interventions to change our trajectory from where the EPA currently project we're going, and we delayed till 2035 to really start reducing, then we'd have to achieve nearly 2 megatons per year to hit that same endpoint. Okay, and the lesson, the reason this chart was in the National Mitigation Plan was to say delay in starting to mitigate makes things much harder. Obviously, these pathways are getting steeper. They're getting more challenging. Okay, but what I want to say is that is true, of course, but the situation is actually significantly, it's more true perhaps than this chart shows. Because as I've just mentioned, what counts here in relation to CO2 is not the end point. It's not what the emissions are in 2050. It's the cumulative emissions between now and then, and the cumulative emissions beyond that. It's the area under the curve. So if you want to ask the question, what's the difference between starting in 2015 and delaying until 2030? Okay, if you delay till 2030, it's no longer enough to aim for the same endpoint, because all this area in between those two pathways is cumulative. Okay, so what you've actually done is overshot the pathway cumulative budget. There's a tacit promise, if we delay, that we're actually going to do significant amounts of negative emissions very quickly. I mean, I said the planet takes a while to heat up, but it only takes a few decades. So the window to reverse course, the window to suck carbon dioxide back out of the atmosphere is not very long. Okay. I stuck this in just because the Climate Change Advisory Council released their annual review just this week, just yesterday, I think, actually. This is essentially almost the same chart. It claims to be exactly the same chart because it says it's for the same group of electricity, built environment, and transport. The numbers are actually different. There's something funny going on there. It appears that there is a discrepancy between the EPA interpretation of that group of sectors and the Climate Change Advisory Council interpretation and the Department of Climate Change, of Communication, Climate Change and Environment interpretation. Hopefully that is going to get resolved soon. But that detailed difference in the exact numbers doesn't really matter. What I want to point out here is that the Climate Change Advisory Council, again, produced this illustrative pathway starting now, and just pointing out that that's much easier than waiting till then. But again, if you wait till then, it's not good enough to just hit the same end point. Okay, you have to do better because you've got to get rid of this area in between the two pathways, the extra emissions that were above your original notional pathway. But I also want to make a slightly policy wonkish point about the CCAC including a linear pathway. Problem with linear pathways, so linear pathways are characterized by the same amount of emissions reductions in tons of CO2 each year, year on year. But if you adopt that kind of pathway, then because your total emissions are going down year on year, then the percentage represented by that fixed amount is getting bigger and bigger. So you're not, if you accept as a very rough proxy for the effort, as you cut emissions, further emissions reductions become progressively harder. Okay, so getting rid of a megaton from the current energy system is one thing. Getting rid of another megaton when you're already down to only 20% of what we currently have or something like that is much, much harder. But that's the implication of a linear pathway. That's the way you're going to do it. So it really backloads the effort. And in the CCAC review, they actually equate this linear pathway, 900 kilotons per year. They say that's the same as 2.4% per year, which is technically true for the first year you do it. But the second year, the percentage reduction is higher. The third year, the percentage reduction is higher. By the time you get to 2040, it would be 5% per year. By the time you get to 2050, it's 12% per year, and you're still not at zero. Okay, and I said you have to get to zero. Okay, so you have to keep on going. So there's actually a lot tied into that choice of a linear pathway, or even that illustration of a linear pathway. It essentially backloads the effort. It says our children are going to be able to do much better than we're able to do, even against a background where an awful lot of reduction has already happened. So the challenge of further reductions is much harder, and incidentally they're having to cope with much more severe climate disruptions, both locally and globally. I think that probably deserves to be revisited. Anyway, okay, we talked about the global quota and we put some numbers on it. How much of that quota is available for Ireland to use? What's our share? What's our fair share? So in our project, we've essentially done a review of the international literature on this topic, and there is a significant international literature now on this topic of what are the appropriate ways of dividing up the global carbon budget. And in very schematic form, there gets bracketed by two approaches. One is called the inertia approach. The inertia approach says, well, if you happen to be a wealthy country that already has high emissions, well, you're kind of locked into that lifestyle. So it's very hard for you to change what you're doing. So there's a certain inertia effect that means because it's so much harder for you to reduce, you should be allowed a bigger share of the budget. The opposite framing is to say, well, all men and women are equal. So equal dibs. Certainly from 2015, when we all signed up to the Paris Agreement globally, from that point on, surely it should be equal shares for all. That's the equity approach. Okay, so the equity approach would give, so Ireland as a relatively high emitting per capita nation, on the inertia approach gets a bigger budget, on the equity approach gets a smaller budget, or quota. We use the word quota for a single national allocation of the global carbon budget. But we've applied these different approaches that are documented in the international literature, and the range you get left for Ireland is somewhere between, say, 600 megatons of CO2 and 1,000 megatons of CO2. It's not much more than that. Depending on your interpretations of equity and historical responsibility, it could actually be argued to be significantly less than 500 megatons. Okay, but certainly that kind of brackets the range. If you think in terms of current annual emissions of CO2 of the order of 40 megatons, that's not an awful lot. It's not an awful lot to get to zero. Okay, to play not a globally leading part, but to play our fair part. And the whole structure of the Paris Agreement relies on individual nations being willing, able to come forward and voluntarily play their fair part. So the first question is to ask ourselves, what is our fair part? Another complicated diagram, these are emission pathways. I've just tried to collapse a whole lot of things onto a single way of looking at things, which is, let's assume you're going to be on some sort of exponential pathway until your budget is exhausted. Okay. Well, if you took the least quota down at this end, the fairest quota, the equity type quota, you see the numbers down at the bottom here. These numbers are saying what's the year-on-year exponential reduction rate, minimum, maximum year-on-year rate of reduction that would correspond to that quota. And you see it varies from about 7% per year down to maybe 4% per year. So that's what we're seeing. So I'm trying to get my pointer back here. That's what we're seeing down here. Okay, so the green line would be a reasonable interpretation of Ireland playing its fair part and progressively spreading out our very limited remaining budget in the best, over the longest period of time, having the least year-on-year emissions reduction rate. But it would mean committing ourselves this year, well, actually committing ourselves last year to a year-on-year, because this is calibrated to 2015, to a year-on-year reduction rate of 7.5%. That's like 3 times the illustrative rate for the first year indicated by the Climate Change Advisory Council. Okay, if you took an inertia point of view, you should say that because we've been emitting so much more up to now, we should be allowed a longer period of time and a bigger budget. Then you might look at 4.4%, a bit above 4%. That's that blue line. But just to say, if you go on the blue line and as time progresses, it becomes clear that we placed our bet in the wrong place and the planet is actually warming up faster than expected, or to get global buy-in, we need to treat equity more fairly than just being generous to ourselves with the inertia budget. If we wind up having to conform to the equity budget, then we would run out of budget, just gone. We have no more emission space left by about 2040. If we flatlined emissions today, we didn't start reducing at all, then we'd run out about 2031, 32. If we followed the current EPA projections, so the with measures projections, as the EPA calls it, we'd run out, that's a slowly still rising, we'd run out about 2030, not 2035. We'd already have used up the full budget by 2030 or so. With extra measures, that's with additional measures, with fewer measures, we'd run out maybe 2029. If you actually take account of what happened in 2016, as I said, these were all premised on starting in 2016. In fact, we didn't start in 2016. Emissions actually went up by about nearly 4% of CO2 in 2016 based on the provisional inventory from the EPA last week. So where we're really at is here. If that was an exponential pathway and we stuck on it, we would have run out as early as 2027, 2028. Okay. What does it mean to say we run out? Does the World Climate Security Force turn up at our ports and immediately shut us down? Of course not. That's not the way the Paris Agreement is set up, and there was no way that international agreement would have been made to allow that to happen. Okay, so what happens is, at that point in time, we become essentially officially in carbon debt to the rest of the world. So you remember our little sovereign debt crisis, the financial sovereign debt crisis. This would be a carbon debt crisis. The implication of the carbon debt crisis, unfortunately, carbon debts are real physical debts. They're physical CO2 in the atmosphere. You can't get rid of them by changing a few numbers in a spreadsheet in a computer. Okay, so this real physical carbon debt, by continuing to emit every single tonne, every day, every week, every month, we go on emitting at the high rates beyond that point, that represents an additional promise to the rest of the global human population that we are going to undo that, and we're going to undo it pretty damn quick. We're going to be able to succeed in pulling that CO2 back out of the atmosphere within a couple of further decades. Okay, so this is the challenge that we're lining up for not children. Anybody who's younger than certainly 45, this is their world. Okay, this is not even young people's problem. This is the majority of our population. And this is the backloading and the procrastination issue that we need to get our heads around. And again, just to be clear, if this sounds like a dire, alarming message, well, yes, it's a dire, alarming message. If it sounds like an alarmist message, well, I'm sorry, I'm just a messenger. Okay, I'm not presenting you anything. This is not Barry McMullen's opinion. I'm not an atmospheric scientist. I'm not a climate scientist. This is not what I do in my day job. Okay, I'm an engineer. This is based on the best scientific understanding that the world community is able to offer. Climate science is the most robustly tested, criticized, assessed, reassessed again, human science that has ever existed. Okay, it's as robust as it gets. Does that mean it's infallible? No. No human knowledge is infallible. Okay, but hopefully as engineers we like to work on the best scientific understanding that we can lay our hands on, and this is the best scientific understanding that we currently have. So as I say, it's not, I wish it were otherwise. Okay, but it's not my message in that sense. Okay, well, we're digging ourselves into a hole. It would be preferable to stop digging. But given that we are digging ourselves into a hole, what are the options? That's what we're having a conversation about. Negative emissions technology is also referred to as carbon dioxide removal, or CDR. You'll see both words out there. There's a complicated chart, but basically on the left-hand side, you've got biological ways of taking CO2 out of the atmosphere. On the right-hand side, you've got more physical and technological ways. So plants photosynthesize, they absorb CO2, through photosynthesis you get carbon-based molecules that represent carbon that has been detached from oxygen and taken out of the atmosphere. Okay, so plants will do this for you. They certainly do it, and there's already a lot of plants doing it. But unfortunately, there's also this fossil carbon, which is, historic or really geologic plants over millions of years that sequestered carbon dioxide out of the atmosphere, turned it into these carbon-based chemicals or forms, what we call fossil fuels, and buried them conveniently in the crust of the planet. But we've started digging them up at a ferocious rate, burning them, getting the CO2 back and putting it back in the atmosphere. So yes, plants in principle are a way of doing this, but there are also technological means. So you can capture carbon dioxide, you can filter it out of atmosphere. It's in very low absolute concentration. You'll hear 400 plus parts per million, 0.04% by volume. It's a trace gas in the atmosphere. It has a dramatic effect on the planetary energy balance, but just in absolute volume terms, it's a trace gas. So separating it from the atmosphere is quite difficult, but it can be done. We know it can be done. We have spacecraft that do this. The space station does it. We have the technology to do this, but it needs energy to do. It needs machinery to do. It costs money to do, but it can be done. There are also some physically CO2 reactive minerals. That's another pathway. If you can expose enough of them to enough atmosphere, then and other required conditions, then you can get a relatively natural process. But you have to intervene technologically to enable that relatively natural process. So you have to capture. Then you have to decide what you do with the captured carbon. With the plants, you can. It has to be stored for a very long time. Okay, not just hundreds of years, but millennia. It has to be very secure storage. So there's biological approaches to that. You can try and store it in the biosphere, essentially. So you can keep forests standing. You can get it into the soil. You can restore ecosystems more generally. You can change your agricultural practices to maximize the rate at which carbon gets placed into the soil. So you wind up with carbon in ecosystems, in standing biomass, above ground biomass, below ground biomass, and in soils. You could also transform it, so you can generate biochar, for example, through pyrolysis, and you can grind that up and incorporate it into soils. You can also take that plant material, and you can use it, you can extract the energy again, so you can burn it for energy, which we currently do, of course. So we burn bioenergy materials, biomass for energy. But then if we want to get negative emissions, if we want to get carbon dioxide removal, then we have to put it somewhere safe. So then you get into whether, and joins with this pathway, we might have extracted CO2, separated it from air. We have to compress it, and we have to store it somewhere, and the usual proposal is to store it in some sort of relatively geologically stable formations underground. We could spend hours going into the fine details of all of these. And now, if you thought that slide was complex, I want to give you the really complex one. Got ahead of myself then. We're about midway through our project. So we've done our first cut using one particular methodology on assessing across all these different methods that are suitable for use in Ireland what the actual capacity is to remove carbon dioxide in Ireland, indigenously in Ireland. The methods we're looking at: bioenergy with carbon capture and storage, I just mentioned at the end there; afforestation, but you keep the trees standing, so you've captured biomass in the trees, you don't cut them down again and burn them or whatever. You capture it into soils by improved farming practices. You use plants to make biochar and you incorporate that into the soil. You use direct air capture combined with carbon dioxide, carbon capture and storage, or enhanced weathering. That's the physical rock process. And you get numbers ranging from, very small numbers in terms of megatons of CO2, a few megatons for enhanced soil carbon sequestration. It gets better, maybe 50 from biochar. Enhancement, that's still in soils. Enhanced weathering, maybe 100 plus. Afforestation, maybe 100 plus. Bioenergy with carbon capture and storage, or direct air capture, carbon capture and storage, the potential might be up into several hundreds of megatons of CO2, but not several thousands of megatons of CO2. Okay, so again, going back to the numbers we saw earlier for the remaining quota for Ireland, where we were seeing numbers between maybe 500 and 1,000, if we could do this, it could add an extra bit of flexibility to our transition. But it doesn't mean we don't have to transition. It maybe buys us another decade. Okay, it's an awful lot of effort, and it doesn't buy us an awful lot of time. Okay, and these, it's not that you can stack all these together. To a certain extent, these are competing with each other. Some of them can be done to a certain extent together. Some of them will compete with each other. So you can't just say we could do all of the above. And again, just the caveat, this is a preliminary evaluation. We've got a long way to go. The project has another year to run. We'll hopefully have better numbers by the time we get to the end. This was the complicated slide. And again, I don't want you to focus on the detail here. What this is about, again, is a preliminary evaluation based on the international literature of the, as it were, attractiveness of these different options. Okay, and it's quite qualitative. So we've got various criteria here, okay, including obvious things like cost, total removal capacity, how ready is the technology or the understanding to do it, how vulnerable is it to future climate change, how vulnerable is it to re-release of the carbon back into the atmosphere, what the energy penalty, if we're trying to decarbonize our energy, we need a whole lot of low carbon energy to remove carbon dioxide from the atmosphere. Then if something has a high energy penalty, that's a problem. Some of these require significant amounts of land to be allocated for them, particularly anything that involves bioenergy. You need land to grow the biomass or the crops for that. So we've got all these different criteria. I say cost is in there, it's only one, and just remember cost is only one factor. And this is the particular set of carbon dioxide removal or negative emissions technologies I mentioned earlier. Ideally, of course, what you'd like to see is a column that is all green. Okay? And you'd say, bingo, we put all our eggs in that basket. Instead of which what you see is, well, there's precious little green, and it's not all in one column. Okay, and even in the column that has the most green, which is the direct air capture with carbon capture and storage, there's 3 very, very red boxes. Okay, there is no good answer here, but there's a lot of complexity in trying to choose the least bad. But again, the message here is that it's a complex business that we're getting into, and we've left it pretty late. As I said, we're talking about both globally and looking at the Irish carbon quota. We're talking about getting into this business on our current trajectory, unless we change course pretty dramatically in terms of the gross emissions that we're still producing. Then we have to change course and get these things operational very, very quickly. A particular topic of study in the project is because bioenergy with carbon capture and storage globally is the approach that is, as it were, most popular in the integrated assessment modelling of climate change. We're putting particular effort into trying to look at the Irish role in that. This is work that was done by Mike about 10 years ago, actually, but we will be revisiting it. But I throw it up here for a particular reason. This is showing essentially the life cycle greenhouse gas emissions associated with different agricultural systems, allocations of land use in Ireland. And the point to get out of this is that if you want to be in the bioenergy basis on a life cycle approach, you want to be in the bioenergy basis business, then there's no point in doing bioenergy if you wind up having a whole lot of emissions associated with it. And that there is that danger. If you have to use intensive nitrogen fertilization, nitrogen fertilizers are energy intensive to produce, okay, and they also lead to nitrous oxide, which itself is a potent greenhouse gas. So you have to look at this in the round. If we're sucking CO2 out of the atmosphere, but we're simultaneously using more energy to make nitrogen fertilizers, or we're releasing nitrous oxide from the land where the fertilizer has been spread, that might all be a wash. So you need these life cycle assessments. So miscanthus and short rotation coppice willow in Irish conditions from that life cycle basis were assessed as the most attractive, but we will be revisiting that within this project. So in particular, the things we'll be doing in the project, we will be focusing on those 2 bioenergy crops. We're going to do something that hasn't been done in Ireland before, which is to use what's called a mechanistic model to assess the potential. There have been a number of studies of the bioenergy potential in Ireland, but none of them to date have used this so-called mechanistic modelling, where you're essentially trying to look at the plant physiology in Irish conditions, and also look at the potential impact on that physiology of projected climate change over the time period that we're looking at. And we will be revisiting, as I say, these greenhouse gas life cycle assessments. So, for example, we know that one of the models, and it's, there probably is high potential, but one of the models for bioenergy in Ireland is biogas from anaerobic digestion. But you have to feed anaerobic digesters with feedstocks. There's various feedstocks, but you need probably at least 50% of so-called dry plant material. And so that currently would likely come from grass, but, well, is the life cycle balance on grass as good as or better than these dedicated bioenergy crops? Okay, I'm going to try and wind my way out of this now as quickly as I can, John. CCS is central to the energy system-based approaches to negative emissions. Whether you're doing bioenergy, carbon capture and storage, or you're doing direct air capture, they both involve carbon capture and storage. And carbon capture and storage is also central to trying to reduce the gross emissions from existing fossil fuel use. Okay, whether that's in existing electricity production or transport and heating if they are electrified. Okay, that just places more pressure on decarbonising electricity. So CCS, and this is the quote from the Energy White Paper 2 years ago, for the medium term, natural gas will remain a critical component in the Irish energy system, electricity system in particular. And it said in this context there may be a role for CCS. Just as a, shall we say, counterpoint to that, I've also added this other, it's not exactly saying a contrary thing, but it's saying a complementary thing. This is a report released just in the last month. The quote is, consequently, in delivering a mitigation program for 2 degrees centigrade, there is categorically no role for bringing additional fossil fuel reserves, including gas, into production. It's too late for gas to be a transition, a bridge in the transition. Okay, we actually do need to be planning to ramp down gas, natural gas. Biogas, another matter. If we can substitute biogas, great. And if the biogas is low emissions biogas, but that has to be a life cycle assessment. So it's a complicated story. I'm going to, this is just CCS, is highlighted in the National Mitigation Plan. And I know that Gas Networks Ireland, for example, and ESB are both looking very hard, and there are probably other energy companies in Ireland already looking hard at getting CCS working on fossil fuel, probably in the first instance gas electricity generation, sooner rather than later. The potential storage site we have down in Kinsale is actually, in global terms, an exceptionally attractive site, comparatively speaking. So I'm told by the people who've looked at it. But I'm emphasising it here because we need to get CCS working, get experience with that, even on fossil fuel generation, so that we're ready to make it work on bioenergy with CCS and direct air capture. A couple of points on the EU policy landscape. The Renewable Energy Directive talks about renewable energies. It doesn't talk about low carbon energies. There's a potential for policy conflict there, and it currently makes no mention of, it talks about bioenergy, but it makes no mention of bioenergy with carbon capture and storage. That should already be in our policy landscape. It shouldn't be being kicked down the road. On the ETS and ESR side, which is the direct emissions reduction as opposed to renewable penetration side of European policy, a significant point is that we need absolute emissions reductions, and the current way that bioenergy is treated, where it's just arbitrarily classified as zero emissions on combustion, doesn't reflect the true physical impact of bioenergy, and it certainly doesn't incorporate the potential land use competition that arises from major expansion in bioenergy. So that there are serious issues still to be answered. On the direct air, I've talked a good bit about bioenergy there. On the direct air capture, this is just a tweet from a couple of weeks ago. A couple of years ago, people told me direct air carbon capture was impossible. Now it's commercial. The only question is getting the price down. This is a picture of a real live direct air capture plant operating commercially. So we're told in Austria or Switzerland possibly. That's Zurich actually, yeah. And it's commercial. Now, you need to read the small print. They're not being paid to capture CO2. Okay, they're being paid for CO2 for product. They've got a customer, and they're choosing to produce that CO2 by direct air capture, and they're just about making in the very specific commercial situation they're in. They're making a business of that, but that's not a scalable model. But it's excellent from a piloting and demonstration point of view. So it's a real thing. The thermodynamics are not great, but it's a real thing. Preliminary conclusions to say we're halfway through the project. Large-scale negative emissions technologies might ease our gross emissions problem. In other words, we feel it's really, really hard to stop putting carbon dioxide into the air. Well, if we could ramp up removals of carbon dioxide, maybe that would help. But removals are also hard. So it's not a magic solution. And anticipatory reliance. In other words, if we decide now, well, it's okay to keep on emitting like there's no tomorrow, because tomorrow we're going to be able to remove it again, that would be a very high risk strategy. Because it may turn out to be impossible or too expensive or impractical. All kinds of things can go wrong. And the risk distribution is highly inequitable. The people at the front end of climate change, really at the front end of climate change, are not living in Ireland. So should we be taking these risks on their behalf? According to the Paris Agreement, we shouldn't, or the Sustainable Development Goals. We do, however, need, our current conclusion is we do need to progress the piloting and the deployment and building up expertise in these technologies, because we need to expand our possibility space. We need as many tools as we can because we're heading into very difficult territory. But they should be viewed as additional to, not a substitute for, really aggressive emissions reductions. I've been tacitly or indirectly talking a little bit about agriculture, but because we're focused here tonight on CO2, I haven't talked about the other greenhouse gases that Ireland in particular has a large loading of, methane and nitrous oxide, from our largely ruminant-based agricultural system. Just to say, it's a complicated question how you weigh up the role of different gases in policy. Currently, we're using a very, very crude instrument to do that. Now, it's the instrument that's agreed at international level, the so-called CO2 equivalence global warming potential measure, but it's a very, very crude instrument. Okay, there would be a lot of sense in, on a policy basis, revisiting that, and Ireland could be pioneering in doing that. But no matter which way you cut it, unless we find ways to scale back the emissions from our agriculture system, then the pressure on the CO2 emissions in the energy system is that much bigger. Okay, it's already very difficult, but if we can't do anything in agriculture, if agricultural emissions continue to expand, and they are expanding, then that makes the problem for the energy system much, much, much harder. Parting thoughts. The carbon that humans are currently releasing has been locked up in the geosphere for hundreds of millions of years and was accumulated in the geosphere over many millions of years. Using the biosphere to capture this geosphere, so we're taking stuff that was safely locked up underground and basically digging it out, burning it, putting it in the atmosphere. And everything I've been talking about is how can we undo that, get carbon dioxide out of the atmosphere and put it somewhere safely underground. Okay, well, actually not continuing, it's already there safely underground. Not continuing to dig it up and put it in the atmosphere would logically be the first thing. And hoping that we're going to store an awful lot of it in the biosphere, that's to say in standing plants, in soil carbon, it's not really realistic because it took millions of years for the amount of carbon that we've been releasing in the last few hundred years to get put into safe storage. And under climate change conditions, there's a real danger it'll get released. This paper just came out today. Again, just to illustrate that this is now the flavour of the month. Everybody wants to talk about negative emissions. The Climate Change Advisory Council. Reliance on technological breakthroughs and significantly reduced costs to enable rapid, substantial and sustained emissions reduction is a high-risk strategy. Okay, we should be doing the stuff, actually being brave about doing the stuff that is lower risk. All right, I said I'd mention our most precious resource. Is it our young people? Is it our intellectual capital? Is it our human knowledge? Is it our solidarity, which is very important? Is it our understanding? Is it our human institutions? The rule of law? These are all terribly important and fragile things, and they're very difficult resources to preserve in turbulent times, which is what we're moving into. But this is our most precious resource. It's the one we have least of. Okay. Thanks to Engineers Ireland for hosting, the Environmental Protection Agency for supporting us, our respective institutions, DCU and Trinity College Dublin. There's our various contact information at the bottom. And we're into questions. And I'll pass these over to my colleagues as much as I can. Okay.
Thank you very much. So thank you for an excellent presentation, Barry. Thank you so much. And definitely an alarming message, if not delivered in an alarmist manner. We definitely won't have anybody at our next event after that, so appreciate that. So maybe just to open up the Q&A, again, like any of these things, Barry, is there opportunities out of this for I would say Ireland in particular, to be a leader on this, as opposed to, in a lot of ways we seem to be a technology adopter or adapter. Is there any, or even like you kind of touched on it towards the end in relation to agriculture, is there something that Ireland can leave an impactful message or impactful way forward that other countries, because again, given the scale of what we are compared to a lot of other countries, so is there an opportunity there for us?
There certainly are opportunities, and I mean, I mentioned Gas Networks Ireland. I don't want to pick on them uniquely, but they're certainly working very hard on both the biogas side and the CCS side, for example. And you put those two things together and you've got BECCS, as long as you're controlling the fugitive emissions and the life cycle and the fertiliser and all of those aspects. So it's not trivial, but there's certainly opportunities. And as a relatively small country, we pride ourselves in being nimble. And I know lots of people complain about Irish government and Irish policy and all of that. It's a popular thing to do. But if you compare our political performance on the political question of the day, Brexit, to our nearest neighbour's political functioning, I think you'd have to say we have an exceptionally functional set of political institutions. So I think if we can get policy and enterprise and citizens, and again, the citizen engagement, the citizen assembly, I think that was world leading. Okay, that was an opportunity on the political side, on the social engagement side. So we are, there's lots of things we're not getting right, but there are things we are getting right, and there's opportunities for us to do a lot more of it.
Jerry Duggan, Irish Academy of Engineering, thank you very much for a very thoughtful presentation, or thought-provoking. Now, two comments and a question. The first one is that the main Kinsale field is about the only defined carbon storage reservoir we have that with a reasonable prospect of utilisation. It has approximately a capacity to accommodate the carbon emissions from about 1,000 megawatts of gas-fired generation for 40 years, which actually isn't a large amount, and yet it's the only resource we have. But the important point is it is likely to be abandoned by the operator within 2 to 3 years. And in the event of it being abandoned without being suitably treated for future use, it will be very difficult to recover the situation. Now, the recent ESB report produced by Pori for them identified the issues there and the institutional difficulties of making carbon capture and storage work, particularly the long-term liability issues associated with who is actually liable if you have a CO2 escape in 500 years. The second comment is, some of you may have been at a lecture here by Paul Dean and I forget the other gentleman, in relation to what they learned in visiting the carbon capture and storage facilities in Alberta. And effectively, in that lecture, they identified that Shell there were dealing with a pure CO2 stream from a hydrogen production facility associated with tar sands production. And even so, the costs of CCS were astronomical. Now, to do it, taking it from the air, in terms of the energy potential involved and everything else, means that you're talking about astronomical squared. So I really think we need to look carefully. The question is, though, if you could go to the grid slide you showed, which was about 5, you described it as being complicated, about 5 before the end. Yeah, that one there. Two things. One is BCCS and DACCS. You indicate the carbon removal is high in one case and very high in the other. Yet in a previous slide, you indicated that both had very much the same potential. I just ask you to have a look at that sometime in the future. But if you'd comment there on EW, which is a technology I'm not familiar with, and in fact, anyone looking at that would say that this is possibly the most prospective technology. Would you or your colleagues care to comment on what's involved in that? Because I'm totally unaware of it.
Okay, thanks, Jerry. Should have been taking notes. The issue about Kinsale, absolutely. Not basically abandoning that and then trying to go back on it a few years later would be silly. In terms of the Irish CCS storage capacity, obviously Kinsale is the front and centre candidate, but the GSI study 10 years ago did identify, a lot of other potential sites. On a global basis, there's lots of other sites. Norway claims that the Sleipner field that they've been storing carbon in for the past 20 years has a huge capacity, and it is possible, it's technically possible to ship CO2 around the world if it comes to that. So many open questions there, absolutely, but not exploiting the opportunity of Kinsale while we can, due to institutional as opposed to technical barriers, would be very disappointing. The question on this, essentially, the BECCS, you've got the storage, so they're both going into CCS. So CCS is one constraint, but where it's coming from, we can get as much air as we like, okay, but we've only got so much land area to plant plants. So that's why the bioenergy BECCS capacity removal potential was qualitatively signalled as lower there than DAX. DAX energetically, I know what you're saying, but I'm told by the people who work on this, was speaking with the director of the UK CCS Research Centre earlier this year. The people who work on this say that the thermodynamics are actually not as bad as you might think. So even though obviously it does take more energy to do it than from, say, a flue gas from a gas station or something like that, where you've got relatively much higher concentration to start with, it is harder. It does take more energy to do, but it doesn't scale linearly. It's a log type relationship. And indeed, I was told, and I'm not vouching for this, but I was told that even burning gas, okay, you could still get as much as 30% of the energy out as electricity while being absolutely carbon zero. That's a combination of CCS taking 90% and direct air capture for the remaining 10%. Okay. Yes, it's expensive. Absolutely. I agree with you. I think, we'd be much better off burning less, a lot less, than trying to do this. But that's very, very difficult to do because so much of our incumbent systems are so tied to doing that. What's your final point? Enhanced weathering. Enhanced weathering, you take certain kinds of rock, olivine rocks, ultra basic rocks, you grind them up. That's energy intensive. But apparently there's an awful lot of this rock on a global basis, and there's quite a lot of it even in Ireland. You quarry it, you grind it up, and you spread it on land, and with moderate rates of spreading, it doesn't interfere with other land use. Now, you can't use it in a forested area, you can't use it in urban areas, but you could use it, it could be incorporated on agricultural land, basically, as part of the practice of managing the agricultural land. You have to keep on spreading it. I'm not sure what the spreading frequency is, but it weathers. Okay, basically it weathers, and as it weathers, it absorbs, so it becomes ultimately carbonate type material, carbonate rock type material. So it's a very stable form of carbon at that stage. But it's a slow, natural process. It happens already. It's a background process on a global basis already. But the idea here is to accelerate it by exposing more surface area, which is why you're grinding it up. So exposing it to air and water, and the process then happens naturally. Beyond that, I can't help. That's the principle of it at any rate. You didn't get any questions online?
Yeah.
Oh, we got another here.
I'm Thomas Hubert from the Farmers Journal. On just a wild question, but is there any research into breaking down the CO2 molecule and storing the carbon separately from the oxygen?
Well, that's technologically, technically it can be done, but it's even more energy intensive because essentially what you wind up with is an energy-rich material. So in fact, so-called synthetic biofuels use a pathway exactly like that. So you produce hydrogen somehow. Now you have to do it a low energy, low carbon way, so you can't do it using natural gas, which is the way we usually produce hydrogen. But there are chemical pathways where you react hydrogen and carbon dioxide, and you wind up with some long carbon chain molecule. Well, short or long, you can produce methane, you can produce methanol, you can produce ethanol, you can go to liquid fuels. But it's all energy in. Okay, so there's a huge inefficiency. So unless you've got some huge access to some huge, very low carbon energy source. I mean, look, the future is unpredictable. If in 10 years' time the work on the fusion energy test bed progressed at completely unexpected speed, and it turned out to be dramatically easier than we had thought, and we were able to build out thousands of fusion power generators so that we had, you know, vastly more energy than we could use, then we could talk about building those sorts of things. We could, you know, we could have synthetic fuels for our aeroplanes, synthetic fuels for our internal combustion cars. That would be magic. But it kind of would be magic. So I don't think we should plan our policy on that kind of basis. That gets back into risk management. Oh, Mike's he's not going to ask a question, he's going to make a comment.
Just add something on that. And basically what you're talking about is artificial photosynthesis. You're trying to take CO2 from the atmosphere and fix it, as plants do. And we've been struggling for a long time to improve on photosynthesis. There is quite a lot of research that's been done on artificial photosynthesis, but there's also been a lot more done on trying to increase the efficiency with which plants can photosynthesize, and therefore fix more CO2, produce more of these plant products, some of which you could store and therefore sequester the carbon. We've made, researchers are making some progress, but it's you know, in order to achieve the sorts of things that we need to do to solve these sorts of problems, you've got a long, long way to go.
I don't know what kind of commentary it is or final message, but engineers in the house will have recognised the famous Swiss railway clock. The distinctive feature of the Swiss railway clock is that when the second hand reaches 12 o'clock, it stops for an extra second. You get an extra spare second once a minute on a Swiss railway clock. I don't know how we can magic up extra time to address the challenges we've got here, but that's kind of what we have to do.
Okay, ladies and gentlemen, just before wrapping up, thank you all for coming. Thank you all for dialing in. There's plenty online as well. There's over 30 or so online, so thank you all. I'd like to thank the Energy Institute as well for co-hosting and co-presenting the night. And again, just finally, thank Barry and the team for coming and contributing. And again, if you could all show your appreciation, and we wrap it up. Thank you all.